I need you to do something for me right now. Stop the video. Go outside. Look up at the moon. Did you do it? No, you didn't. You kept watching. That's okay. Most people won't either. We're all too busy, too distracted, too comfortable in our understanding of the world. But here's what you would have seen if you'd looked up. A crime scene. That pale, quiet disk hanging in the night sky? It's not a lamp. It's not a natural satellite that gently formed alongside Earth like some cosmic companion. It's a scar. It's the shattered remains of a planetary collision so violent, so impossibly catastrophic, that it should have ended everything. Instead, it created the one thing that makes you, yes, you sitting there right now, possible. You think you know how Earth formed. You learned it in school. Gas cloud, gravity, planets, done. Simple, clean, boring. That story is a lie. Not because it's wrong, but because it's incomplete. It's like telling the story of your birth by saying, cells divided. Technically true. Completely missing the point. The real story? The real story is that you're standing on a planet that defies the rules of physics, a planet that shouldn't exist, wasn't supposed to survive, and has been trying to kill everything on its surface for 4.6 billion years, and yet here you are, alive, conscious, scrolling through YouTube on a device that contains more computing power than existed on the entire planet 50 years ago. Watching a video about cosmic origins while probably ignoring 17 other notifications. You are the result of the most improbable sequence of events in the history of the universe. And I'm going to prove it. What you're about to watch is different from any other documentary you've seen. This isn't a dry recitation of facts. This isn't Carl Sagan poetry about billions and billions. This is the complete, unfiltered, raw story of how a cloud of gas became you. We're going to spend the next 90 minutes, maybe longer, maybe much longer if you're brave enough, reconstructing the most chaotic, violent, beautiful accident in history. We're going to start with a cloud so enormous, your brain will literally hurt trying to picture it. We're going to watch that cloud collapse, ignite, and spin out the solar system like cosmic pizza dough. We're going to witness Earth get hit by another planet, a Mars-sized world named Theia, that slammed into our infant world at 40,000 kilometers per hour and somehow, impossibly, didn't destroy everything. We're going to solve the mystery of where the oceans came from, a detective story involving hydrogen isotopes, asteroid water, and one meteorite that fell on a Sunday morning in rural Australia and changed everything we thought we knew. We're going to survive the late heavy bombardment when Earth was a cosmic shooting gallery being pummeled by asteroids large enough to boil away the oceans repeatedly. We're going to watch the first spark of life emerge from the chemistry of a dead world and debate whether that spark came from deep-sea vents, tidal pools, or whether it arrived from space itself riding inside a rock from Mars. And we're going to explore the stories humans told for thousands of years before science existed, the myths and legends that imagined Earth carved from a giant's corpse, churned from a cosmic ocean, or spoken into existence by divine command. Not as quaint superstitions, but as humanity's first profound attempts to answer the same question we're still asking. Where did we come from? And finally, and this is where it gets truly weird, we're going to confront the possibility that none of this is real. That Earth, the solar system, your entire existence might be code running in a simulation created by entities we can't comprehend for purposes we can't imagine. Here's our problem. We weren't there. Nobody was there 4.6 billion years ago to film the formation of Earth. There are no witnesses, no surveillance footage, no black box recorder documenting the collision that created the moon. All we have are clues. Ancient rocks that formed before Earth existed, floating in space, waiting to crash into our atmosphere so we can study them. The strange, perfect spacing of planetary orbits that reveals the ghost of a process long since finished. The chemical fingerprint of water in our oceans, a signature written in deuterium ratios that tells us which cosmic delivery service brought the ocean. The moon itself, that massive scar hanging overhead, its cratered face, a permanent record of the violence that forged our world. And what we're going to do? What humanity has spent centuries doing is take all those scattered clues, all that ancient, melted, broken rock, and reconstruct the crime scene. We're going to work backward from the evidence to build a single, coherent narrative that explains how we got here. But here's the thing you need to understand before we start. That simple story you learned in school, the one about the Nebular Hypothesis and planetary accretion, that's just chapter 1. It's the foundation, the beginning, the tutorial level of cosmic formation. To truly understand Earth's origin, we need to read the whole book. We need to go deeper than any documentary has taken you before. We need to visit the failed theories, the beautiful, elegant explanations that turned out to be wrong, but taught us how to think about planetary formation. We need to honor the ancient myths, not as quaint superstitions, but as humanity's first profound attempts to answer the same question we're still asking. Where did we come from? And we need to accept that the more we learn, the stranger the universe becomes. So, let's go back in time, way, way back, 4.6 billion years ago. You can't even picture that number. It's not like 1,000 years, it's not like a million. It's a number so huge, it loses all meaning. But that's the starting point. And where we start isn't a planet, or a star, or anything solid at all. We start with a cloud. Not a puffy white cloud like you see on a summer day. This cloud was massive. It was unimaginably, ridiculously massive. We're talking about a cloud of gas and dust floating in some forgotten corner of our galaxy, the Milky Way. This wasn't just a regular cloud. This was the original stuff, the raw, basic ingredients for everything you know. Think about that for a second. Immanuel Kant, a German philosopher, a guy with a huge white wig, thought this up back in 1755. He just looked up and wondered, what if the sun and the planets all started as one giant, swirling, beautiful cloud of dust? That's the core of it. We call it the Nebular Hypothesis. It's the story every scientist accepts as the foundation. Now, how big was this cloud? Try to picture it. If you could somehow shrink down to the size of a dust mote and stand on the edge of this cloud, you wouldn't see the other side. You couldn't see the other side even if you had a telescope. It was maybe 100 times bigger than our current solar system. Our sun, Jupiter, Earth, Mars, everything. It would all fit in this cloud, and there would be tons of empty space left over. It was mostly hydrogen, the simplest, lightest stuff in the whole universe, the basic, fundamental building block of all matter. But mixed in there were little bits of heavier elements. Where did those come from? They came from exploded stars. That's a cool thought. The iron in your blood, the gold in your jewelry, the silicon in your phone. It was all created inside the heart of a giant star that lived, died, and then exploded in a massive cosmic fireworks show billions of years before our sun even existed. All that stardust, all those leftovers were just chilling in this giant, cold cloud, minding their own business. Nothing much happening, just a giant, boring, cosmic blob. But then, something changed. Something disturbed the peace. We don't know exactly what, but we can make some really good guesses. Maybe a star close by went supernova. A supernova is a star exploding so violently that it can literally rip the fabric of space. That explosion would have sent a shockwave ripping through the galaxy, and when it hit our little gas cloud, it squeezed it. It compressed it. Or maybe the cloud just got so enormous, so ridiculously big, that its own gravity finally won. Gravity is the ultimate force in the universe. It's always trying to pull things together. When the cloud got big enough, its own gravity started pulling the edges in, pulling all those hydrogen atoms and bits of stardust toward the center. It was like a giant cosmic sigh. The whole thing started to collapse in on itself. This collapse wasn't a slow, gentle drift. It was a massive, system-wide, unstoppable process. And here's where the physics gets really cool. As the cloud shrank, it didn't just get smaller, it started to spin. Think about a figure skater on the ice. When they're spinning slowly, their arms are stretched out wide. But the moment they pull their arms in close to their body, they suddenly start spinning way faster. That's a basic law of physics, the conservation of angular momentum. The same thing happened to our cloud. As the material got pulled in toward the center, the whole thing started spinning faster and faster and faster. As it spun, two things happened simultaneously, like two sides of the same cosmic coin. First, the center of the spinning cloud got denser and hotter. All that material piling up, all those atoms rubbing against each other, created immense heat and pressure. It was all being squished into a tiny space. Second, the outer parts of the cloud flattened out into a disk. Imagine you're making a pizza. You take the dough and you spin it. It doesn't stay a lump, it flattens out into a wide, thin circle. Our solar system literally started as spinning pizza dough, except this pizza was destined to become the sun, the earth, Jupiter, and everything else. This enormous, rotating disk of cosmic dust and gas. The center of that disk, the very middle, kept getting hotter and hotter. The temperature climbed past 1,000,000 degrees, past 5,000,000 degrees, until it hit about 10 million degrees Celsius. That is heat beyond imagining. At that critical temperature, the pressure was so insane that something fundamental changed. The hydrogen atoms, the simple building blocks, started to smash together with such force that they fused. They turned into helium, a different element. And when they did that, they released a completely massive, ridiculous amount of energy. That energy pushed back against the crushing force of gravity, and the center of the disk ignited. It flared to life. Congratulations! You just made the sun. A massive, glorious, fiery engine of light and heat that was now the gravitational anchor for everything else in the spinning disk. It was the birth of our star, the moment our solar system became what it is today. But the real magic, the part that makes us possible, was happening in the leftovers. Around that newborn sun, in that giant spinning disk of cosmic debris, the planet-building factory was now open. It was a chaotic, spectacular construction zone. In this cosmic snow globe, we had tiny particles of dust and ice constantly bumping into each other. Think about static electricity. When you rub a balloon on your hair, the little charged bits of matter want to stick together. The same thing was happening in space. Tiny dust particles would bump into each other, and sometimes, through static electricity or weak molecular forces, they would stick. They would adhere. Grain by grain, these cosmic snowballs started to grow. They went from being the size of a grain of sand to the size of a pebble. Pebbles stuck together to form rocks. Rocks stuck together to form boulders. It was slow. Incredibly slow at first. We're talking thousands, even millions of years for a pebble to become a boulder. But it was unstoppable. The temperature was the key to what was built where. Close to the fiery, scorching hot sun, the heat was so intense that any ice or lightweight gases would just immediately vaporize. Only the tough stuff could survive: rocky materials and metal. That's why the 4 planets closest to the sun, Mercury, Venus, Earth, and Mars, ended up being the small, dense, rocky planets. They were built from the leftover metal and rock that could handle the heat. But venture further out, way out, into the cosmic suburbs, the story changes completely. Out there, the temperatures were frigid. They were bone-chillingly cold. So, ice and gas could stick around. Massive amounts of hydrogen, helium, water ice, methane ice, carbon dioxide ice. It was a massive, frozen supply of building material. The growing bodies out there could hoover up not just rock and metal, but gas and ice too. That's why you ended up with the massive gas giants, Jupiter, Saturn, Uranus, and Neptune. They became enormous because they had so much more material to work with. They're basically giant, cold, crushing balls of gas with a small, rocky core hidden deep inside. Our home, Earth, formed in a sweet spot. Scientists call it the Goldilocks zone. You've heard the story. Not too hot, not too cold, but just right for one incredible thing: liquid water. It was the perfect distance from the sun. Not so close that all the water immediately boiled away and evaporated, and not so far that it all instantly froze into a miles-thick layer of ice. The temperatures were just right for oceans to eventually form. For millions of years, Earth was under construction. Tens of millions of years. It wasn't a peaceful, smooth process. It was a demolition derby. Countless chunks of rock and metal crashed together in spectacular, violent collisions. Every single impact added mass to the growing planet. Every piece added weight, made it bigger, made its gravity stronger. But those impacts also generated an incredible amount of heat. Imagine smashing a piece of metal with a huge hammer over and over again. The energy of the impact turns into heat. On a planetary scale, this happened so much and with such intensity that the whole planet got so hot, so completely molten, that it literally melted. It became a giant, glowing, seething ball of liquid rock, a massive, beautiful, terrifying inferno. This heat allowed the heavy stuff, the iron and nickel, to sink down to the very center, forming our planet's incredibly dense, metallic core. The lighter rocky stuff floated up to the surface, where it would eventually cool and solidify to become the first solid crust. What makes this story so powerful, so compelling, is how much it explains it. It answers all the basic questions about our neighborhood. Why do all the planets orbit the sun in the same direction? Because they all formed from a single spinning disk that was rotating one way. Why are most planetary orbits on roughly the same plane? Same reason. The pizza dough flattened out and all the toppings formed on that flat surface. Why do we find similar elements throughout the solar system? Because it all came from the same... And here's the part that ties it back to the present day. We can actually watch this process happening right now. Space telescopes like Hubble and the James Webb are aimed at other young stars, and what do they see? Planetary disks. They see the spinning pizza dough. They see dust grains clumping together. They see these disks in various stages of formation. We are literally watching other Earths being born right now in distant corners of the galaxy. It's like having a time machine that lets you look at our planet's baby photos. The Nebular Hypothesis is not just some old, dusty theory from the 1700s. It's rock-solid, confirmed science. It is the foundation of everything, from a massive cold cloud to a living world in just about 50 million years. That sounds like forever to us, but in cosmic terms, that's barely a blink of an eye. The unexpected story. The astronomer who almost got fired. Here's something most people don't know. Pierre-Simon Laplace, the mathematician who refined Kant's nebular hypothesis in 1796, almost lost his position because of it. Napoleon Bonaparte himself challenged Laplace, asking why his mathematical model of the solar system's formation made no mention of God as the creator. Laplace's response became legendary. "Sire, I had no need of that hypothesis." This wasn't arrogance. It was the birth of modern cosmology. For the first time in human history, someone had proposed a completely naturalistic mechanism for planetary formation that worked without divine intervention. The equations didn't care about theology. Gravity was enough. Napoleon reportedly laughed and told the story to everyone at court, but his colleagues were horrified. Many thought his career was over. Instead, his mathematical model became the foundation of everything we know today. Sometimes the most dangerous ideas are the ones that work too well. I'll be honest with you. Every time I try to truly comprehend 4.6 billion years, I fail. My brain just stops. I can say the number, I can write it down, but I cannot feel it. I think about my grandfather who died before I was born, and that feels impossibly distant. That was only decades ago. This is billions of years, millions of generations of stars living and dying before our sun even existed. Sometimes late at night, I'll step outside and look up and I'll really try to wrap my mind around the fact that the calcium in my bones was forged in a supernova that exploded before Earth existed, that I am literally made of dead stars. And I feel so small, it almost hurts. But then I realize I'm a part of this story. We all are. We're the universe becoming aware of itself, asking questions about its own birth. And somehow, that makes the incomprehensible scale feel meaningful. Like maybe we're small, but we're not insignificant. Think of the solar system's formation like this. Imagine you're at a massive outdoor concert and someone spills an entire pitcher of beer. At first, it's just a spreading puddle, but then someone bumps into the table and it starts spinning. The liquid flattens out into a disc with most of the beer rushing toward a depression in the center where it pools. Small bits of food, pretzels, chips, crumbs, start sticking together in the liquid, slowly forming larger clumps as they orbit the central beer puddle. The biggest clumps sweep up all the smaller debris in their path. Eventually, you've got one massive, gross central blob, the sun, a few medium-sized clumps of pretzel matter orbiting nearby, the rocky planets, and absolutely enormous, soggy masses of chips and ice further out, the gas giants. The whole thing is spinning, flattened, organized by nothing more than gravity and momentum. Our entire solar system is basically a spinning beer spill that got organized, except instead of pretzels, it's planets, and instead of beer, it's hydrogen and stardust. But the principle? Exactly the same. But here's what we haven't answered yet. If this violent construction site was so hot that it should have boiled away all the water, how did Earth end up 71% covered in oceans? And what happened next that was so catastrophic that it should have destroyed everything? Stay with me, because the next chapter is where things truly get insane. So we have a planet. It's built up. It's a molten hot ball of liquid rock and metal, spinning in orbit around the new sun. Things should be settling down, right? The building is over. Time for the cooling to begin. Wrong. This is the part of the story that sounds like pure science fiction. The part that proves the Earth you're standing on is an absolute fluke. Because the very next thing that happened to our newborn planet was an event that should have ended everything. It was the single most catastrophic, ridiculous, planet-shattering collision in our entire history. It's how we got the moon. This is called the giant impact hypothesis. Back in 1975, two scientists, William Hartmann and Donald Davis, dropped this bombshell. They proposed that our moon wasn't formed on its own, and it wasn't captured. It was born from a colossal, unimaginable smash-up. Picture this: Earth about 4.5 billion years ago. Still young, still hot, still glowing. But it wasn't alone in its orbit. It was playing a very, very dangerous game of cosmic tag with another world. This other world was roughly the size of Mars. Not a small asteroid, not a comet, but a whole planet. Scientists named this doomed world Theia, after the Greek Titan who was the mother of the moon goddess. For millions of years, these two planets, Earth and Theia, shared the same orbital path, like two cars driving side by side, but slowly, inevitably getting closer. Their orbits were becoming more and more unstable. Everyone knew deep down what was coming. It was the ultimate, inescapable cosmic pileup. The inevitable collision happened. Theia slammed into Earth at a ridiculous speed, maybe 40,000 kilometers per hour. Try to imagine the energy of that impact. Take every car crash you have ever seen in your life, every explosion, every catastrophic disaster, and multiply the total energy by about 1 trillion. That's the scale we're talking about. It wasn't just a big crash. It was an event so violent, it literally changed the fundamental physics of our planet. But here's the key: the scientific fluke that saved us. It wasn't a head-on collision. If Theia had hit Earth head-on, it would have destroyed both worlds, vaporizing them into a cloud of scattered material that would never coalesce into anything stable. Instead, it was a glancing blow. Think of a giant cosmic billiard ball shot. Theia hit Earth at an angle, shearing off a massive amount of material from both worlds, but leaving the Earth's core mostly intact. The impact was so extreme, so ridiculously powerful, that it fundamentally rewrote the rules for Earth. First, it completely slowed our planet's rotation. Earth's day used to be super fast, maybe only 6 hours long. The impact dragged on the planet, slowing that insane spin down to our current 24-hour day. Imagine that. The reason you have a morning and a night is because of this one giant accident. Second, the collision tilted our planet's axis by 23.5 degrees. Why do you have seasons? Why is summer different from winter? It's because the Earth is tilted. That tilt, which makes life on Earth so diverse and beautiful, was created by Theia. The heat generated by the crash was so immense that both worlds partially melted and mixed together like a cosmic silly putty. But the truly wild part of the story is what was blasted into space. The impact blasted enormous chunks of both planets, Earth's mantle, and Theia's entire body into the surrounding space. It created a massive, glowing, spectacular ring of debris around the Earth. For a brief, shining moment in cosmic history, our planet looked like Saturn. We were surrounded by a ring system made not of tiny ice crystals, but of molten rock and metal. This ring was ridiculously hot, probably glowing yellow-white like a giant, dangerous neon sign visible from space. It was the most beautiful, violent sight you could imagine. Over the next incredibly short period, short in geologic time anyway, maybe just a few thousand years, gravity went to work. The larger chunks in the ring started pulling in the smaller ones. They started coalescing, they started collecting. Slowly, rapidly, the debris ring began to coalesce into our familiar companion. The moon was born surprisingly quickly. The whole process, from impact to a mostly solid moon, took maybe just a few centuries. This hypothesis is so elegant because it explains all the weird things about the moon. Why do the moon rocks brought back by the Apollo astronauts have almost the exact same chemical composition as Earth's mantle? Because the moon is literally made from Earth's insides mixed with the remains of Theia. It's Earth's flesh and blood blasted into space and reformed. Why does the moon have such a small iron core compared to Earth? Because most of Theia's iron core merged with Earth during the collision, not the moon. The moon was built mostly from the light crustal material. And why is the Earth-Moon system so energetic? Why do we spin and orbit so energetically? Because that enormous collision transferred incredible rotational energy to both worlds. The momentum is still there, still driving the tides and slowing our rotation even today. But here is the most incredible part, the twist that makes it all a miracle. That ancient catastrophe made life on Earth possible. Without the moon's massive gravitational pull, our planet would wobble chaotically on its axis. Our tilt would swing wildly, causing extreme, impossible climate changes that would have prevented life from ever getting started or would have immediately destroyed it. The moon acts like a giant cosmic anchor, stabilizing our rotation. It also creates the tides, the rhythmic rise and fall of the oceans, which may have helped early life forms transition from the sea to the land billions of years ago. A constant push and pull, a constant rhythm. Every time you look up at that pale, quiet orb, remember this. You are seeing the result of the single most important traffic accident in our planet's history. One that created a beautiful scar, and that scar quite literally made our world the perfect, stable, life-giving place for us to flourish. For decades, after Hartman and Davis proposed their wild theory, most scientists thought it was too dramatic, too unlikely. The math seemed impossible. Then, in 2001, a team at the University of Colorado ran the most detailed computer simulation ever attempted of planetary collisions. They plugged in the mass of early Earth, the estimated mass of Theia, various impact angles and speeds. They let the computer crunch through the physics of trillions of particles interacting under gravity over millions of simulated years. When the results came back, everyone in the lab went silent. The simulation showed that a glancing blow at exactly 45 degrees would produce a moon with the right mass, the right orbit, the right composition, and the right lack of iron core. But here's the eerie part. The simulation also showed that this perfect angle happens in only about 3 to 5% of all possible planetary collisions. If Theia had hit us at 40 degrees or 50 degrees, we wouldn't have a moon. We'd have a debris ring or nothing at all, or Earth would have been completely destroyed. The computer proved that our existence depends on an impact that was accurate to within a few degrees out of a full 360-degree possibility. We are the product of a cosmic billiard shot that had to be nearly perfect. One of the researchers later said, "We're not just lucky, we're impossibly lucky." I have a confession. I used to be terrified of the moon. When I was about 7 years old, I learned that the moon is slowly drifting away from Earth, about 3.8 centimeters per year. I did the math, badly because I was 7, and calculated that in my lifetime the moon would be gone. I had nightmares about looking up and seeing nothing but empty black sky, about the Earth wobbling and seasons becoming chaos. My mom tried to explain that it would take billions of years, but I didn't understand billions. I just knew that the thing that made the tides, the thing that lit up the night, was leaving. It felt like abandonment on a cosmic scale. Now, decades later, I understand the physics. The moon isn't going anywhere in any human timescale. But sometimes late at night, when I see it hanging there, I still feel that childhood anxiety. A reminder that nothing in this universe is truly permanent. Everything we love, even our faithful companion that's been with us for 4.5 billion years, is slowly drifting away. We're all temporary, even moons. Understanding the giant impact requires thinking about momentum transfer. Imagine you're standing still, holding a basketball, and someone throws a bowling ball at you from the side. If they hit you straight on, you're both going down in a messy pile. But if the bowling ball just clips your shoulder at an angle, something remarkable happens. You spin around, the bowling ball careens off in a new direction, and pieces of both of you, theoretically, go flying in a third direction. That glancing blow transfers energy in multiple directions simultaneously. Some stays with you, making you spin. Some goes with the impactor, Thea's core merging with Earth. And some goes flying off, the debris that became the moon. The giant impact wasn't a head-on crash. It was the universe's most consequential sideswiping. Earth got spun around, gained mass, got a permanent limp, the tilt, and threw up material that became our companion, all from being clipped in just the right way at just the right angle by another planet playing cosmic bumper cars. But here's the question that should be keeping you up at night. We've explained how Earth formed and how it got its moon, but we still haven't answered the most important question. How did this violent molten ball of rock become a water world? Where did the oceans come from, and why didn't they all boil away? The answer involves a cosmic delivery service, a chemical detective story, and evidence that's quite literally falling from the sky right now.
Okay, so the planet is built, and it's been hit by another planet, and we have a moon. Now we need to step back and look at the actual construction method in extreme detail. Long before humans figured out how to stack stone blocks, the universe was already an expert at cosmic construction. This method is called accretion theory. It's the description of how the Earth grew from things smaller than your hair into a full-sized, molten world. It was the ultimate building project, one that took tens of millions of years and involved more construction materials than we could ever imagine, all flying through space. The core idea behind accretion is simple. Things stick together. But the mathematics behind it, worked out by people like the Soviet scientist Viktor Safronov in the 1960s, is ridiculously complex. Safronov's ideas completely revolutionized how we think about building planets. It's so fundamental now that it's taught in every single science class that deals with planets. The story starts again in that giant spinning disk around the young sun, the one we talked about before. But this time, we're starting tiny, really, really small. We're talking about dust grains, smaller than the width of a human hair. These grains are made of rock, metal, and ice, and they're all just floating around in the cosmic equivalent of a giant, messy snow globe. At first, the growth is painfully slow. These tiny particles are zipping around at different speeds, and when they bump into each other, they don't crash and shatter every time. Sometimes they stick together. Why? Because of weak forces, like static electricity, or the slight attraction between molecules, what scientists call van der Waals forces. Think about the dust bunnies that form under your bed. They're just small bits of fluff that have stuck together. This is the same principle, but it's happening on a cosmic scale. These space dust bunnies are floating in zero gravity, and they are destined to become mountains. Over thousands of years, the microscopic dust grains become pebbles. The pebbles become boulders. The boulders become objects that are basically floating mountains of rock and metal. This is the phase that requires incredible cosmic patience. If you could watch this process, it would make watching grass grow look like an entire Formula One race. It is ridiculously, unbelievably slow. Growth happens on a timescale that completely breaks your human understanding of time. But then, a truly remarkable moment happens, a game changer. When one of these growing objects reaches about a kilometer in size, a little over half a mile across, suddenly it has enough mass that its own gravity starts to kick in. It's no longer relying only on static electricity to grab material. Now its gravity is powerful enough to pull in anything that gets close. This is the point of no return. These kilometer-sized objects are called planetesimals. The word means tiny planet. They become the cosmic vacuum cleaners. They start sweeping up everything in their orbital paths, clearing out the dusty ring around the sun. And now the growth rate explodes. Instead of doubling in size over 1,000,000 years, a planetesimal might double in size every few thousand years. The larger it gets, the stronger its gravity becomes, and the more material it can capture. It's the ultimate example of a snowball rolling down a hill. It gets bigger and bigger, faster and faster, until it becomes an unstoppable planetary juggernaut. It's the rich getting richer, but with gravity. In Earth's orbital zone, hundreds, maybe thousands of these planetesimals were competing. The early solar system was basically a cosmic demolition derby. They were crashing into each other constantly. Sometimes they would stick together to form an even larger object, an ultimate merger that created more mass and more heat. Other times the collision would be too fast, and they would shatter into thousands of smaller pieces that would then be swept up later by the winners of the competition. Earth, Venus, Mars, these were the survivors of that ultimate battle royal. The final stage of accretion was the most violent and most awesome. It was the point where the largest objects in Earth's neighborhood, maybe a dozen or so bodies, some the size of Mars, some even bigger, engaged in the ultimate planetary showdown. These final collisions weren't gentle taps. They were so energetic, so unbelievably powerful that they could melt entire planets. Each impact did two things. It added mass to the Earth, making it bigger, and it simultaneously heated it up by turning the energy of the crash, the kinetic energy, directly into heat. By the end of this process, Earth had grown to its current size. And because of all that relentless, insane heating from all those impacts, the whole planet was completely molten. A giant, glowing, seething ball of liquid rock, with temperatures easily over 2,000 degrees Celsius. The final result was the planet we have today, a world built entirely from the crashing, sticking, and melting of countless cosmic pebbles and rocks. It's a construction story built on pure, relentless, gravitational violence. Here's something that blows my mind. Viktor Safronov, the Soviet scientist who gave us the mathematical framework for planetary accretion, initially proposed a theory that was spectacularly, embarrassingly wrong. In the 1950s, he calculated that it would take approximately 10 billion years for planets to form through gradual accretion, more than twice the age of the solar system. His peers ripped him apart. The evidence from meteorites showed planets formed in less than 100 million years. Safronov could have abandoned his work. Instead, he did something remarkable. He went back and asked, "What am I missing?" He discovered he drastically underestimated the role of gravitational focusing, the way a growing planetesimal's gravity actively pulls in material from a much wider area than its physical size. When he corrected this single error, his timescales dropped from 10 billion years to 50 to 100 million years. Suddenly everything worked. His revised calculations from 1969 are still the foundation of planetary formation theory today. The lesson? Sometimes being spectacularly wrong is the fastest path to being right. Safronov's willingness to admit his mistake and fix it gave us the mathematical tools to understand how every rocky planet in the universe is built. I sometimes wonder if humans would care more about space if we could watch planets form in real time. Because the truth is, even as someone who spent years studying this stuff, I struggle with the timescales. 10 million years for a pebble to become a boulder? I can't even maintain focus for 10 minutes sometimes. We're a species built for immediate cause and effect. I hit the light switch, the light comes on. I drop something, it falls. But planetary formation? It's like trying to watch continental drift with your naked eyes. You can't see it happening, so your brain refuses to believe it's real. I've stood in museums staring at meteorites, actual pieces of planetesimals that failed to become planets, and tried to feel the connection. But it's hard. These rocks are older than our planet. They were bumping around in the solar nebula while Earth was still under construction, and I'm just some guy who barely remembers where he parked his car. Sometimes I feel like the universe is so vast, so slow, so incomprehensible that maybe we're not meant to understand it.
Maybe we're too small, too fast-lived, too impatient. But then I remember we figured it out anyway. We took equations and evidence and imagination, and we reconstructed billions of years of cosmic construction. We're temporary, but we're not helpless. Think of planetary accretion like compound interest in a bank account. You start with 1 penny. At first, the growth is invisible. After a year, maybe you have $1.01, barely noticeable. But the interest compounds. Your dollar earns interest on itself, then the interest earns interest. After a few years, you have $10, then $100, then suddenly you're at $1,000 and the growth accelerates dramatically. Each dollar you have now is pulling in more dollars. The rich get richer. Planetary accretion works the same way, except instead of dollars earning interest, it's mass attracting mass through gravity. A dust grain becomes a pebble, 1 cent becomes $1. The pebble becomes a boulder, $1 becomes $100. Once you hit planetesimal size, that critical 1 kilometer threshold, it's like hitting $10,000 in your account. Suddenly your gravity is strong enough that you're not just waiting for random collisions anymore, you're actively pulling in material from a huge radius. You've hit the exponential growth phase. And just like compound interest, the longer it runs, the more explosive the growth becomes. Earth didn't form gradually at a steady rate. It formed slowly at first, then faster and faster until in the final few million years, it was swallowing Mars-sized planets whole. The rich don't just get richer, they devour everything around them. But here's the mystery that still haunts planetary scientists. During this violent construction process, Earth should have been completely dry. The heat was so intense that any water should have been vaporized and blown away by solar wind. And yet somehow, we ended up with enough water to cover 71% of our surface. So where did it come from? Who delivered the oceans? And why does the answer involve a decades-long detective story about hydrogen isotopes? Buckle up, because this is where things get really weird.
Okay, so we have a planet, a big, hot, rocky planet. We have a moon, thanks to the massive accident, but the Earth is a world of fire and rock. Where is the water? Where did the oceans come from? Because without the oceans, there is no life. The planet is 71% covered in water. That is a completely massive, ridiculous amount of H2O. But our planet formed so close to the sun that the temperatures should have been way too hot for water ice to survive. Any water that was originally there should have been boiled off and blown away into space. So the question remains, who made the delivery? For decades, scientists had two main ideas, two competing theories about the cosmic delivery truck that brought the life-giving liquid. They were a detective story that hinged on a tiny little thing, a chemical fingerprint. The first suspect in the case was the comet. Comets are basically dirty snowballs. They're massive mixtures of rock, dust, and all sorts of ice, mostly water ice, left over from the solar system's formation. They live way out in the cold depths where water can stay frozen solid for billions of years. When a comet swings close to the sun, the ice turns into vapor, creating those spectacular glowing tails we see in the night sky. The math seemed to work out beautifully at first. Earth needed about 1.4 billion cubic kilometers of water to fill its oceans. During the late heavy bombardment, the cosmic shooting gallery we'll talk about next, millions of comets were hitting our planet. It seemed like an open and shut case. Comets delivered the water, problem solved. But science has a frustrating way of complicating beautiful theories. In the 1990s, space missions started actually analyzing the composition of comet water. Water molecules come in a couple of different flavors. You have regular hydrogen, and you have its heavier cousin, deuterium. Earth's oceans have a very specific ratio of these two. It's like a chemical DNA fingerprint that tells you where the water was born. When scientists measured this ratio in the water from comets like Halley's Comet and Hale-Bopp, they found something completely unexpected. Comet water had about twice as much deuterium as Earth's oceans. This was a major, huge problem. If most of Earth's water came from comets, our oceans should have the same chemical signature. It was like the DNA evidence didn't match the prime suspect in the cosmic murder mystery. It sent everyone scrambling. Maybe there were different types of comets. Maybe early Earth changed the ratio somehow. The plots thickened even more when the European Space Agency's Rosetta mission studied Comet 67P up close. That comet's water had even higher deuterium content. If that comet was representative, then comets could have contributed maybe only 10% of our water. They were helping, but they weren't the main delivery service. But then, a major twist happened. In 2011, a telescope analyzed Comet Hartley 2 and found something completely remarkable. Its water had almost exactly the same isotopic composition as Earth's oceans. Suddenly, the comet theory was back on the table. It suggested that not all comets are the same. Maybe Earth's water came from a very specific population of comets that had formed closer to Jupiter and Saturn before being flung out into the far reaches of the solar system. These specific comets, when they came raining down, delivered water with just the right chemical signature to match our oceans. The comet delivery also helps explain why our oceans contain so many organic compounds, the complex carbon-based molecules that are essential for life. Comets aren't just water ice. They're also a massive delivery service for the ready-made starter kit for biology. While comets were getting all the attention and all the drama, a quieter, much more scientifically solid revolution was happening with asteroids. For most of history, these rocky chunks were seen as dry, dusty leftovers, nothing more than bone-dry metal and stone. But starting in the 1990s, scientists discovered that many asteroids are actually soaking wet. They contain significant amounts of water, not as loose ice, but locked up in minerals and chemical compounds. It's water that's chemically bound into rock crystals. And here is the smoking gun moment, the chemical fingerprint of asteroid water. Remember how comet water had too much deuterium? Well, water extracted from carbonaceous chondrite meteorites, pieces of these water-rich asteroids that have fallen to Earth, have isotopic ratios that match our oceans almost perfectly. It was like the detective finally found the real prime suspect and the DNA was an exact match. The timing also made much more sense. Comets mainly arrived after the planet was formed during the late heavy bombardment, but asteroids were part of the original construction crew. They were delivering water continuously throughout Earth's formation, mixing the water directly into the building materials. It was a much more gentle, slow-drip irrigation system. As the Earth grew through the accretion of countless water-rich asteroids, the water was gradually incorporated into the planet's entire interior. Later, things like volcanic outgassing and other geological processes brought that water up to the surface, where it finally condensed to form the first oceans. Space missions have completely confirmed this. The Japanese Hayabusa missions and NASA's OSIRIS-REx mission brought back samples from asteroids like Ryugu and Bennu, and they showed clear evidence of ancient water activity, minerals that could only have formed in the presence of liquid water. Even more dramatically, the largest asteroid series shows what looks like water geysers erupting from its surface. It's literally an ocean world hiding under a rocky crust. The asteroid hypothesis also explains something absolutely huge: the deep water inside Earth. Geological evidence suggests that Earth's mantle, the layer beneath the crust, contains several times more water than all the surface oceans combined. That deep water is exactly what you would expect if the asteroids delivered H2O right from the very beginning, incorporating it into the rocky interior. The verdict. Today, most scientists agree the water came from a combination of sources, but that asteroids probably provided the majority of Earth's water. It was a cosmic collaboration, where the quieter, more rock-based delivery service gave us most of our water, and the dramatic, icy comets came in later with a valuable secondary delivery of organic compounds and a little extra liquid. The water in your glass? It likely started its journey in a water-rich asteroid billions of years ago.
In 1969, on September 28th, something extraordinary happened in the small town of Murchison, Australia. A bright fireball streaked across the morning sky and exploded, showering the area with over 100 kilograms of meteorite fragments. At first, it seemed like just another space rock. But when scientists analyzed the Murchison meteorite, they discovered something that would revolutionize our understanding of Earth's water. The rock contained over 70 different amino acids, the building blocks of proteins, and nearly 12% water by weight, locked inside mineral crystals. But here's the truly shocking part. The water's deuterium ratio was nearly identical to Earth's oceans. This single meteorite this random space rock that happened to fall on a Sunday morning in rural Australia provided the smoking gun evidence that asteroids had delivered our oceans. Even more remarkable, the Murchison meteorite contained complex organic molecules that formed the basis of cell membranes. It wasn't just water. It was a complete chemistry set for life, preserved in pristine condition for 4.6 billion years, waiting to be analyzed by curious humans in a small Australian town. One rock changed everything we thought we knew about the origin of life on Earth. Every time I drink a glass of water, I try to remember where it came from. I really do. I stand there at the kitchen sink and think, this molecule traveled across the solar system in a rock. It survived the formation of Earth. It's been a cloud, a raindrop, a river, maybe part of a dinosaur, maybe part of an ocean, maybe inside a million other living things. But you know what actually happens? I just drink it without thinking, because my brain can't hold both realities at once, the cosmic significance and the mundane thirst. I want to live in constant awe of the fact that I'm 60% stardust water that came from asteroids. But I also need to pay my bills and remember to buy groceries. Sometimes I feel like I'm failing at appreciating the miracle, like I'm too distracted by being human to properly honor the fact that I'm made of cosmos. Maybe that's okay, though. Maybe the universe doesn't need me to be constantly amazed. Maybe it's enough that sometimes, standing at my sink at 2 a.m. when I can't sleep, I remember, this water is older than mountains, older than life itself, and for just a second, I feel connected to something impossibly ancient and beautiful. Then I go back to bed, because even cosmic water can't fix insomnia. Understanding how Earth got its water is like solving a crime where the murder weapon keeps changing shape. Imagine detectives arrive at a crime scene and find water everywhere, pools of it, covering 71% of the floor. They know someone delivered it, but who? The first suspect is a dramatic character, the comet, who enters rooms with flashy ice tails and a flair for spectacle. I brought the water, the comet insists. But then forensics runs a chemical test, the deuterium fingerprint, and it doesn't match. The comet's water signature is all wrong, twice as heavy as the water at the scene. Case closed? Not quite. Because then investigators discover a quieter suspect lurking in the background, the asteroid. Boring, rocky, unsexy asteroid. Nobody suspected them because they don't look like they're carrying water. But when scientists crack them open, they find the asteroids are soaking wet inside, and their water signature matches perfectly. It's the classic detective story twist. The obvious, flashy suspect didn't do it. The quiet, overlooked one did. Except in this case, the crime was delivering the gift of oceans, and both suspects probably worked together. Asteroids providing the bulk shipment, comets adding the organic chemistry finishing touches. Earth's water came from the cosmic equivalent of a team effort between the flashy extrovert and the reliable introvert. But here's what nobody tells you about Earth's early history. Just when the water finally arrived and the oceans started to form, the universe decided to test our planet one more time. Around 3.9 billion years ago, something triggered an absolute apocalypse, a cosmic shooting gallery that nearly sterilized our world. Why did it happen? And how did life manage to survive? The answer involves Jupiter, Saturn, and the most violent 200 million years in Earth's history.
Now that we have a planet with its moon and its water, you'd think the drama would be over. You'd think the solar system would finally settle down into a peaceful neighborhood. But science discovered the opposite. In the 1970s, scientists studying the moon rocks brought back by the Apollo missions found something that made absolutely no sense. The samples showed evidence of a massive cataclysmic spike in asteroid and comet impacts that happened about 3.9 billion years ago. This was long after the solar system should have cleared out. This discovery led to the theory of the late heavy bombardment. Picture the world again. 4 billion years ago, Earth has oceans, it has a crust. Life might have even been starting to appear in those early seas. And then, without warning, all hell broke loose again. Something caused a sudden, ridiculous surge in the number of asteroids and comets crashing into the inner planets. This wasn't a few extra shooting stars. This was an apocalyptic bombardment that lasted for about 200 million years. The moon's surface still bears witness to this cosmic shooting gallery. Those massive impact basins like Mare Imbrium are scars from this very period. The question is, what triggered this absolute chaos so long after the solar system had supposedly been built? The answer lies far away with the outer planets, Jupiter and Saturn. Computer models suggest that around 4 billion years ago, these two massive gas giants entered a gravitational resonance. Their orbital periods, the time it takes for them to go around the Sun, became perfectly synchronized in a way that massively amplified their gravitational effects on smaller objects. This synchronization was like flipping a switch on a cosmic pinball machine. Jupiter, the massive gravitational bully, began flinging asteroids and comets out of their stable orbits, sending them careening through the inner solar system like celestial cannonballs. Some were ejected from the solar system entirely. Others, unfortunately for us, were sent crashing toward the Sun. Earth, being a huge target, took a massive, repeated beating. The scale of this bombardment is nearly impossible to comprehend. Scientists estimate that at the peak of this period, Earth was being hit by objects larger than 20 kilometers across at least once every few million years. The largest impacts created craters hundreds of kilometers wide and temporarily turned parts of our planet's surface into molten rock. The energy from these collisions was so intense that it could have boiled away Earth's oceans multiple times, completely vaporized them into the atmosphere. This has profound implications for the history of life. If the bombardment was this severe, it might have sterilized our planet's surface repeatedly, forcing any early life forms to survive only in deep underground refuges or around the super-hot underwater hydrothermal vents. Scientists call this the impact frustration of early evolution. Life kept trying to get started, only to be hammered back into hiding by the next big apocalyptic impact. But here's the silver lining, the twist that makes this violence a necessary evil. The late heavy bombardment might not have been entirely bad for life. The smaller impacts, the comets and water-rich asteroids, could have been continuously restocking our planet with crucial ingredients. The same cosmic bombardment that kept sterilizing the surface was also bringing in fresh water, organic compounds, and other materials that early life needed. It was a cycle of death and desperate, sudden rebirth. The most compelling part is the timing. The bombardment eventually tapered off, and what do we find in the geological record? The earliest evidence of life on Earth, microbial fossils and chemical signatures, dates to around 3.8 billion years ago, shortly after the worst of the LHB ended. It's as if our planet's surface had to be thoroughly churned up, melted, boiled, and reprocessed before it finally became stable enough for biology to take hold and begin its long evolutionary journey. Every living thing on Earth is descended from the survivors of this cosmic trial by fire. Here's something wild. We almost didn't discover the late heavy bombardment at all. When NASA was planning the Apollo missions in the 1960s, there was a huge debate about whether to bring back moon rocks or just take pictures. Rocks are heavy, and weight meant less fuel for the return journey, which meant more risk to the astronauts. Some engineers argued that photos and sensors would tell us everything we needed to know. But a small group of geologists fought back, insisting that you cannot do geology from photographs alone. They barely won the argument. When Apollo 11 landed in 1969, Neil Armstrong and Buzz Aldrin collected 21.5 kilograms of lunar samples, and it changed everything. Those rocks showed clear evidence of intense melting and impact fracturing dating to 3.9 billion years ago. By Apollo 17, scientists knew they were seeing a pattern. Every single landing site showed the same catastrophic scarring from the same time period. If NASA had decided to save weight and skip the rock collection, we might still not know about the late heavy bombardment. We wouldn't understand that life on Earth survived an apocalypse, all because a few geologists refused to compromise on bringing back rocks. Sometimes the weight you carry determines what truth you discover. I think about extinction a lot, maybe too much. Not the dinosaurs, I mean us. Every time I read about the late heavy bombardment, I'm reminded that Earth has been repeatedly sterilized. Life survived by hiding deep underground or in boiling oceanic vents, holding on by its fingernails while the surface world burned. And I wonder, what are we doing to prepare for the next catastrophic impact? Because it's not if, it's when. Statistically, Earth will be hit by another large asteroid. Maybe not in my lifetime, maybe not in my children's lifetime, but eventually. And unlike early microbial life, we can't hide in hydrothermal vents. We've built this entire fragile civilization on the surface. Sometimes late at night, I look up at the sky and think, we're the first species in Earth's history that knows this threat exists, that can track near-Earth objects, that has the theoretical technology to deflect an impact. We're the first life forms who could actually prevent the next mass extinction. But we're not acting like we have forever. We're acting like we have forever. The late heavy bombardment taught life on Earth that nowhere is permanently safe. I just wish we'd learned that lesson before we need it. Imagine Earth during the late heavy bombardment as a person trying to build a sandcastle on a beach while someone is actively throwing rocks at them. You carefully shape the walls, dig the moat, add the towers, then wham! A rock smashes into your castle and flattens half of it. You rebuild. You add details. You make it better. Wham! Another rock, bigger this time, obliterates everything and fills your moat with debris. But you're stubborn. You start again, and again, and again. For 200 million years, this is Earth. Every time life started organizing itself, forming complex chemistry, maybe even early cells, wham! A 20-kilometer asteroid vaporizes the oceans and melts the crust. Start over. But here's the remarkable part. You keep building. Each time you build faster because you're learning. You find ways to protect your castle. You dig it deeper into the sand. You hide the foundation below the surface where the rocks can't reach. Eventually, the person throwing rocks gets tired or runs out of ammunition. The bombardment ends. And when you finally look at your castle, scarred, rebuilt 1,000 times but still standing, it's stronger and more beautiful than anything you could have built if nobody had ever thrown rocks at all. Earth's surface was destroyed over and over, but life didn't just survive the bombardment, it was forged by it. But here's the ultimate question. Once the bombardment finally ended and Earth settled into relative peace, how did we cross the line from dead chemistry to living biology? How did we go from sterile oceans to the first self-replicating organism? The answer involves one of the most controversial theories in all of science, and it might mean life on Earth didn't actually begin here at all.
So, we have the ingredients. We have a stable, water-covered planet. The violence is mostly stopped. Now comes the most mind-bending question of all, the ultimate mystery. How did we go from non-living chemistry to the first self-replicating life? This process is called abiogenesis, literally, life from non-life. This is the moment Earth officially became a living world. The classic, most famous experiment that started all this was back in 1952 with a young student named Stanley Miller. Miller, under his professor's guidance, had a wild idea. What if he could recreate the conditions of early Earth and see if life could spontaneously emerge? He filled a sealed glass apparatus with what scientists thought was early Earth's atmosphere: methane, ammonia, hydrogen, and water vapor. Then he zapped it with electrical sparks to simulate the constant, violent lightning strikes that would have been common on the young planet. After running the experiment for just 1 week, the water in his apparatus turned a murky, reddish-brown. When he analyzed the contents,
he found something absolutely extraordinary. Amino acids. These are the fundamental building blocks of proteins, and therefore, the building blocks of life itself. The basic chemicals of life had formed spontaneously under early Earth conditions. The building blocks are inevitable. The story begins on early Earth, maybe 3.8 billion years ago. We have stable oceans, not the clear blue seas of today, but a vast, rich chemical soup. It's full of organic compounds delivered by those comets and asteroids, constantly stirred by volcanoes, lightning, and UV radiation from the sun. In this primordial broth, simple organic molecules are constantly bumping into each other. They're sticking together. They're growing into larger, more complex structures. But the step to life is the hardest one. You need a molecule that can do the one thing that separates living from non-living, the ability to make copies of itself. Self-replication. Over millions of years, some of these molecular combinations develop this ability. The most promising candidate for the very first replicator is RNA. We know about DNA, but RNA is cooler. It's thought that early life was based entirely on RNA molecules because they can do two things. They can store genetic information, like DNA, and they can catalyze chemical reactions, like proteins. This is called the RNA world hypothesis. Over time, these simple RNA systems evolved the ability to make two new things: proteins, which were better at running the body's processes, and DNA, which was better at storing the precious information reliably. But the original spark, the original simple self-copying molecule, was RNA. But where did this happen? Scientists are still fighting over the location. One of the most compelling places is deep-sea hydrothermal vents. These are underwater geysers where superheated mineral-rich water erupts from the sea floor. When scientists first discovered these in the 1970s, they were amazed. Life thrives there, completely cut off from the sun, extracting energy from chemical reactions instead of sunlight. This is called chemosynthesis. The bacteria at these vents eat stuff like hydrogen sulfide, which is toxic to almost everything else. Why are they a good candidate? Because they offer the perfect, stable nursery. The deep ocean was protected from the violent radiation and impacts happening on the surface. The vents provided a constant, steady source of energy and raw materials, all those dissolved metals and sulfur compounds. The heat was immense. The most primitive organisms on Earth's family tree, the ones at the very root, are often thermophiles, organisms that love extreme heat, preferring temperatures well above boiling point. This makes perfect sense if life originated in the scorching environment around a deep-sea hydrothermal vent. The mineral structures around the vents might have even acted like natural test tubes, concentrating and organizing organic molecules long before the first actual cells evolved. It's the ultimate cradle of life, where geology and biology intersect. Now for the most audacious, wild idea: panspermia. What if life on Earth didn't actually originate here at all? What if it arrived from space? This idea suggests that life is a cosmic phenomenon, something that spreads from world to world like seeds on the wind. This theory gained serious attention when researchers started finding organic compounds and amino acids in meteorites, building blocks delivered fresh from space. But the real clincher was the discovery of extremophile organisms, life forms that thrive in absolutely killer conditions. We found bacteria living in boiling acid springs in the frozen wastes of Antarctica, and most importantly, some bacteria were found to survive direct exposure to the cold, vacuum, and radiation of space for years without dying. If microscopic life can survive the harsh journey through space, then maybe it really could travel from planet to planet, seeding new worlds with the gift of biology. Mars and Earth regularly exchange material. Asteroid impacts on Mars blast rock fragments into space, and some of those fragments land on Earth as meteorites. If Mars ever harbored life, and there's growing evidence that it might have, then some of that life could have made the journey to Earth billions of years ago, riding inside a protective rocky cocoon. This is called local panspermia, and it seems much more plausible than life coming from another star system entirely. The idea is simple. Life only needs to originate once in the galaxy. After that first Genesis event, panspermia could carry that life to millions of other planets, making all life a cosmic family tree.
In 2020, Japanese scientists reported something that should have been impossible. They had attached colonies of the bacterium Deinococcus radiodurans to the outside of the International Space Station and left them there for 3 years, exposed to hard vacuum, cosmic radiation, temperature swings from negative 150 C to a plus 120 degrees C, and zero atmospheric protection. The experiment was designed to test whether life could survive space travel. When they brought the samples back, everyone expected them to be dead. They weren't. The bacteria in the deepest layers of the colony had survived. Not just survived, they had actually reproduced during the journey, forming protective layers that shielded the interior cells. The outer bacteria died and formed a protective shield, while the inner ones thrived. This experiment proved that panspermia is physically possible. Life can survive being blasted into space, traveling between worlds and arriving intact. The implications are staggering. If life originated on Mars first, which some scientists think might have happened since Mars cooled faster than Earth, then every living thing on Earth, including you, might be Martian in origin. We might all be aliens who forgot where we came from. I don't know if I'll ever know how life began. I don't mean humanity collectively, I mean me personally. I've read dozens of papers on abiogenesis, watched countless lectures, interviewed scientists, and you know what? The more I learn, the less certain I become. Was it RNA in a tidal pool? Was it deep-sea vents? Was it delivered from space? Each theory has evidence. Each has problems. Sometimes I envy people with simple answers, like God created life, or it was obviously hydrothermal vents. I don't have that certainty. I'm stuck in the uncertainty. And honestly, it's uncomfortable. I want to know. I want to understand the exact moment chemistry became biology, the precise conditions, the specific molecules. But maybe I won't. Maybe nobody will in my lifetime. And I'm trying to be okay with that, with living in a universe full of questions I'll never get answers to. My grandmother used to say, not knowing is part of the adventure. I'm trying to believe her, but some nights the not knowing feels less like adventure and more like standing at the edge of an infinite ocean in the dark, knowing there's something profound out there but never being able to touch it. Understanding the origin of life is like trying to figure out how a fire started after the entire forest has already burned down and regrown twice. You arrive at a massive forest full of diverse life, oak trees, pine trees, ferns, mushrooms, and someone says, figure out how the very first spark happened 3.8 billion years ago. You can't go back in time. You can't watch it happen. All you have are clues, charcoal deep in the soil, patterns in the growth rings, chemical traces in ancient rocks. You can build controlled fires in labs like Miller did and see how they spread, but is your modern fire really the same as that ancient spark? Maybe the original fire started from lightning, the hydrothermal vent hypothesis. Maybe a burning ember from a different forest blew in on the wind and ignited this one, panspermia. Maybe there were multiple small fires that eventually merged, multiple origins of life. The evidence is fragmentary, burned, transformed by time. You'll probably never know for certain exactly how that first spark ignited, but you can narrow it down. You can rule out impossible scenarios. You can build models that match the evidence. And maybe, just maybe, one day you'll recreate the conditions so perfectly that life spontaneously emerges in your lab, and you'll finally know, yes, this is how it happened. Until then, you're a detective investigating the oldest cold case in history, where all the witnesses are dead and the crime scene has been destroyed and rebuilt 1 billion times over. But before we can talk about how life evolved, we need to address something uncomfortable. What about all the other theories, the ones that almost worked, the beautiful, elegant explanations that turned out to be wrong? Because science isn't a straight path to truth, it's a graveyard of almost correct ideas. And some of those dead theories are so compelling, so dramatic, that they deserve their moment in the spotlight before we move on.
The scientific method is brutal. It doesn't care how beautiful your theory is. It only cares if it matches the evidence. Over the last few centuries, brilliant scientists have come up with some amazing, dramatic ideas for how the Earth was born. But they all got put on the shelf when better evidence came along. We have to talk about them, though, because they show just how hard this problem has been to solve. They're the cosmic ghosts of science, the theories that were almost right. Back in the early 1900s, there was this extremely dramatic idea proposed by two smart British scientists, James Jeans and Harold Jeffreys. They looked at the sun and said, what if the Earth was born from a cosmic near miss? They called it the tidal theory, and it was super popular for decades. Picture the sun, 4.6 billion years ago, burning alone in space. No planets, nothing, just a solitary star minding its own business, fusing hydrogen in its core. Then, out of the cosmic darkness, another star comes wandering through our neighborhood. Not close enough to crash, that would have been way too messy, but close enough to create gravitational chaos on an unimaginable scale. As this rogue star approached our sun, its massive gravitational pull started to deform our sun's shape. Think about the sun being pulled like taffy. Massive tidal forces, the same kind of force that causes ocean tides on Earth, but billions of times stronger, started pulling huge amounts of material right off the sun's surface. Jeans and Jeffreys calculated that if a star passed close enough, it could literally tear off an enormous chunk of solar material. This material wasn't a small flare. It was a long, cigar-shaped filament of hot gas stretching like a cosmic bridge between the two stars. This filament was what would become our solar system. The material would cool and condense, and the thickest part of the cigar, the middle where the gravitational pull was strongest, would naturally form the largest planets, Jupiter and Saturn. The thinner ends would form the smaller planets, like Earth and Mars. It was a beautiful, elegant story that explained why the gas giants are big and the rocky planets are small. The entire architecture of our solar system was the result of this single dramatic encounter with a passing stranger. But why did this dramatic theory fail? Two main reasons. First, temperature. The material ripped from the sun would be so unbelievably hot that it wouldn't cool and condense into planets. It would just immediately expand into space and dissipate. The sun's gravity couldn't hold on to it. Second, these stellar close encounters are too rare. For the theory to work, solar systems like ours had to be incredibly unique in the universe. But now, we know from telescopes watching other stars that planetary systems are actually quite common. They must be the result of common natural processes, not incredibly rare cosmic accidents. The theory was abandoned because the universe turned out to work differently than even the smartest people of the time could imagine. Now for another dramatic story, capture theory. What if Earth wasn't born around our sun at all? What if it was a cosmic wanderer, a rogue planet that formed somewhere else in the galaxy and was later captured by our sun's gravity? It's the story of Earth as an adopted child of the solar system. The idea came from realizing how chaotic the early universe was. Stars weren't born alone. They were born in massive, crowded clusters. In those stellar nurseries, planets were constantly being flung out of their orbits, sent careening through the cold, empty void between stars. This is a rogue planet. Picture young Earth, still warm from its original formation, tumbling alone through the eternal darkness of interstellar space. No sun to warm it, it would have quickly frozen solid, a ball of ice miles thick. For millions, maybe even billions of years, this rogue Earth might have wandered, occasionally passing by other star systems, but never close enough to be captured. The physics of gravitational capture are incredibly difficult. A rogue planet is usually moving way too fast. It would just swing around the star and continue its journey. But in very specific circumstances, maybe if it ran into a binary star system, two stars orbiting each other, or got tangled up in the gravity of existing planets, it might slow down just enough for our sun to capture it. The rogue planet would finally find a home. This theory also seemed to explain weird things like the backward spin of Venus or the crazy tilt of Uranus. Maybe they were all rogue planets captured at different angles. But, just like the tidal theory, capture theory ran into massive problems. The process is too improbable. Computer simulations showed that gravitational capture is unbelievably rare. It can't account for the many planets we see around other stars. And the chemical evidence argues against it.
Earth's rock composition perfectly matches the meteorites formed in our part of the solar system. If Earth had formed around a different star, its rocks would have a different chemical fingerprint, a different isotopic signature. It was a beautiful, romantic story, but the rocks don't lie. Our planet was born here, in a massive, messy construction zone, not captured from a distant, forgotten stellar system. Here's something fascinating. Capture theory isn't completely dead. While it doesn't explain Earth's origin, astronomers have actually discovered real rogue planets wandering through interstellar space. In 2011, telescopes detected what appeared to be Jupiter-sized worlds drifting alone in the darkness between stars, orphans ejected from their home systems. Even more remarkably, in 2020, scientists proposed that a hypothetical planet 9 in our outer solar system, if it exists, might actually be a captured rogue planet from another star system. The evidence is circumstantial. Planet 9 has never been directly observed, but its theoretical orbit is so weird, so tilted compared to everything else, that capture is one of the few explanations that makes sense. So while capture theory failed to explain Earth, it might still explain the farthest, strangest members of our solar family. Sometimes a wrong theory for one thing turns out to be the right theory for something else. Science is full of ideas that were rejected, filed away, and then pulled back out decades later when new evidence emerged. The theories we bury aren't always dead. Sometimes they're just sleeping, waiting for their moment to rise again. I think about failure scientifically a lot. How many brilliant people spent their entire careers championing theories that turned out to be wrong? James Jeans was knighted for his contributions to science. Harold Jeffreys won the Copley Medal, the highest honor the Royal Society can give. These weren't crackpots. They were the best minds of their generation, and they were wrong. Their life's work ended up in the failed theory section of textbooks. That terrifies me, because I write about science, I explain it, I try to understand it, but what if the theories I'm presenting today end up in the same graveyard 50 years from now? What if future generations look back and laugh at how confidently we declared things that turned out to be completely false? I want to believe we finally got it right, that the Nebular Hypothesis and accretion theory and the giant impact are all correct. The evidence is overwhelming, but Jeans and Jeffreys thought they had it right too. They had evidence, they had math, they had the respect of their peers, and they were still wrong. Maybe humility is the only honest response to the universe. Maybe we can only say, this is what the evidence suggests right now, and accept that future discoveries might completely overturn everything we think we know. It's uncomfortable, but it's honest. Failed scientific theories are like early drafts of a novel. Imagine a writer working on the greatest story ever told, the story of Earth formation. The first draft, title theory, is dramatic and compelling. Two stars have a close encounter, material gets ripped away, planets form from the debris. It's exciting, it has action, but when the editor, experimental evidence, reads it, they point out plot holes. This material would be too hot. This encounter would be too rare. The story doesn't match what we observe in other star systems. So the writer scraps it and starts a second draft, capture theory. Earth is a lonely wanderer adopted by our sun. It's romantic, it's melancholy, but again the editor finds problems. The chemical fingerprints don't match, the physics of capture doesn't work, you're forcing the plot. Finally, after many drafts, the writer lands on the version that works. Nebular Hypothesis, a spinning cloud of gas and dust that naturally flattens and forms planets. It's less dramatic than the stellar near miss, less romantic than the cosmic orphan, but it matches all the evidence. The final draft isn't always the most exciting one, it's the one that's true. But here's the important part. You couldn't have written the final draft without all those failed attempts. Each wrong theory taught scientists what doesn't work, which narrowed down what does. The failed theories weren't wasted effort. They were necessary steps on the path to understanding. Sometimes you have to write the wrong story 50 times before you can write the right one. But here's what's really wild. Before modern science gave us these failed theories, humanity had thousands of years to imagine how Earth formed. And the stories they created, the myths, the legends, the creation accounts, are sometimes more beautiful and profound than anything science has produced. So let's do something unusual. Let's honor those ancient stories, not as primitive superstition, but as humanity's first attempts to answer the biggest question of all.
The science is one thing. It's beautiful, chaotic, and true. But for all of human history, before we had telescopes and computer models, we had stories. Humans have this deep, deep need to know where they came from. So all over the world, in every civilization, people came up with their own answers. They are not science, but they tell us a huge amount about ourselves and how we see the world. And these stories are beautiful. They explain why we are here and what we are meant to do. In the Western world, the most influential story of all comes from the ancient text, the Book of Genesis. It's the story that says Earth wasn't formed over billions of years of cosmic accidents. It was created in 6 days by an all-powerful God. The story is famous because it starts with the most famous opening line in all of literature. In the beginning, God created the heavens and the earth. This wasn't a gradual process. This was a rapid, perfect sequence of creative acts, each done by divine command. On the first day, there was just darkness, and God said, "Let there be light," and there was light. He separated the light from the darkness. On the second day, he made the sky and separated the waters above from the waters below. The third day is when our planet started to look like home. God commanded the waters to gather together so that dry land could appear. He called the dry land earth and the gathered waters seas. And then on the same day, God caused the earth to bring forth all the vegetation, the grass, the herbs, and the fruit trees, each one producing seed. This is a story of intentionality and design. Earth wasn't formed through random chance. Every single feature was deliberately crafted for a specific, intended purpose, to be the perfect home for the creatures God planned to place upon it. Then on the fourth day, God created the sun, moon, and stars. Now, for us, this sequence seems backward. We know the stars and the sun formed before Earth, but the biblical account tells the story from Earth's perspective. It prioritizes the view from the ground, where the light exists before the sun becomes visible through the atmosphere. The fifth day brought the first living creatures, the birds to fly in the air and the sea creatures to populate the oceans. And finally, on the sixth day, God created the land animals. And then, last of all, humans, who were given control over all other life on Earth. The creation was completed in 6 days, and on the seventh day, God rested, establishing the pattern for the week that most of humanity still follows today. For the billions of people who believe this, it is the literal truth about how Earth came to exist. It's a completely different kind of story from the scientific ones. Science tells you how things happen through gravity, heat, and chemistry. This story tells you why it happened. Earth exists not as a random accident in an indifferent universe, but as a carefully designed home for humanity, created by a loving God who declared his creation very good. It is a story of purpose. Thousands of years ago, the ancient Greeks crafted one of the most beautiful stories of all. Their way of understanding the beginning of the universe gave us concepts and names we still use today, including the very idea of chaos and the name of our planet as a living entity, Gaia. According to their ancient poet Hesiod, everything began with chaos. Not chaos as in disorder, but a primordial void, a yawning emptiness that existed before anything else. It wasn't nothingness, but rather a state of pure potential, pregnant with all the possibilities that would eventually become reality. And from this primordial chaos, the first actual beings emerged. The first was Gaia, the Earth. She didn't have to be created by anyone. She spontaneously emerged from the void as a living, breathing entity. She wasn't a passive planet like the one in modern science. Gaia was a goddess with her own consciousness, desires, and will. She was literally Mother Earth, capable of giving birth to mountains, seas, and even entire races of divine beings. Her first act was incredible. She gave birth to Uranus, the starry sky, without any male partner. Uranus became both her son and her husband. She also created the mountains and the primordial sea, but their marriage was a disaster. Uranus was a terrible father who hated his children, the Titans, and pushed them back into Gaia's womb as soon as they were born. This caused Gaia tremendous pain, and this cosmic family dysfunction led to the first great conflict. Gaia, suffering, fashioned a great sickle and convinced her son Kronos to ambush his father Uranus. When Uranus next came to embrace Gaia, Kronos attacked him, severing his genitals and casting him into the sea. This violent act, this separation of earth and sky, was what finally allowed space for the world as we know it to exist. The habitable world existed in the space between Gaia below and the dome of Uranus above. The core idea here is that Earth is alive. Gaia wasn't just dirt and rock, she was a complex system that included the atmosphere, the oceans, and all living things. This idea of Earth as a single integrated organism anticipates modern concepts like the Gaia hypothesis proposed by scientist James Lovelock, who suggested that the Earth's biosphere functions like one massive organism, regulating temperature and atmosphere for its own survival. For the Greeks, when you walked on the ground, you were walking on a conscious goddess who suffered, loved, and fought to protect her children. The Norse people, living in the frozen, harsh environment of medieval Scandinavia, crafted one of the most brutal and physical creation myths ever conceived. According to their stories, the Earth wasn't formed through divine commands or cosmic dust. It was literally carved from the corpse of a primordial giant named Ymir. This is not a metaphor. They believed every mountain, ocean, and cloud was once part of a living, breathing creature. The story begins in Ginnungagap, the yawning void between two primordial realms, Muspelheim, the land of fire in the south, and Niflheim, the world of ice and mist in the north. When the heat from the fire met the cold from the ice, the interaction created the first living being, Ymir, the ancestor of all the frost giants. Ymir was a chaotic, massive being. The melting ice also formed Audhumla, the primordial cow whose milk sustained Ymir. As the cow licked the salty ice blocks, she gradually freed another being, Buri, the ancestor of the gods. Buri's grandsons were the three divine brothers, Odin, Vili, and Ve. The three gods looked upon the chaotic realm ruled by the frost giants and decided something had to change. The world was too wild. So they made a decision that echoes with violence. They would kill Ymir and create the world from his remains. The battle was apocalyptic. When Ymir finally fell, so much blood poured from his wounds that it created a great flood that drowned nearly all the frost giants. Then the real work began. The three brothers dragged Ymir's massive, gigantic corpse to the center of the void and started the gruesome task of world-building. From his flesh, they formed the earth itself. Every mountain, plain, and valley was carved from the giant's body. The Norse believed that when you walked on solid ground, you were literally treading on the flesh of this ancient giant. His blood became the seas, lakes, and rivers that flow across the world. His bones were broken and shaped into the mountains and cliffs. His massive skull was used to form the dome of the sky, and to hold it up, they placed 4 dwarves at the cardinal directions, north, south, east, and west, names we still use today. The giant's brains were scattered across the sky to become the clouds that drift overhead. His hair became the forests and vegetation. Even his eyelashes were used to create a protective wall called Midgard, the realm of humans. The Norse creation myth is incredible for its unclinching acceptance of violence as a creative force. It insists that something must die for something new to be born. It perfectly reflects the harsh realities of life in medieval Scandinavia. The world wasn't a peaceful garden. It was built from death and struggle. The mountains are the bones of a giant their gods had to kill. It's a materialistic, visceral, and absolutely unforgettable creation story. In the vast philosophical tradition of Hinduism, the creation of Earth is part of a constantly repeating, cyclical universe. Worlds are created, sustained, and destroyed in an endless repetition. It's a story of cosmic time on a scale that makes the Big Bang look like a blink. The most enduring image is this: the Earth resting on the back of a cosmic turtle, which itself stands on a giant serpent floating in the primordial ocean. It's the ultimate foundation. The creation of the Earth often comes from the story of the cosmic churning, or Samudra Manthan. The gods, Devas, and the demons, Asuras, decided to work together to churn the cosmic ocean to obtain Amrita, the nectar of immortality. For this massive task, they needed a churning rod and a rope. Mount Mandara became their churning rod, and Vasuki, the king of serpents, served as the rope wrapped around the mountain. But the mountain was so heavy it started to sink into the cosmic ocean. This is where Kurma, the turtle avatar of the god Vishnu, comes in. Vishnu transformed himself into a gigantic turtle and dove to the bottom of the ocean, allowing the gods and demons to wrest Mount Mandara on his shell. With this stable foundation, the ultimate foundation, the churning could begin. The churning was a massive recycling project that produced everything needed for the world. First came a terrible poison that threatened to destroy all creation, which the god Shiva swallowed to save the universe. Then came the divine gifts, the wish-fulfilling cow, the goddess of wealth, and finally the nectar of immortality. The cosmic turtle, Kurma, doesn't just appear for one event. In many traditions, he continues to support the Earth on his shell throughout the current cosmic age. He represents stability, patience, and the slow, steady progress of cosmic evolution. The cosmic serpent, Shesha, is equally important, often depicted as the one upon whom Vishnu rests during the cosmic night between world cycles. The serpent represents both the end and the beginning, the continuous, never-ending cycle of cosmic time. This story tells us that our universe, our Earth, is just one of countless universes that have existed and will exist. Creation and destruction are simply different phases in an eternal, ongoing cycle. It's a perspective that sees time as a spiral and Earth as a point of stability resting on the back of a patient, divine turtle in an endless ocean of potential. Along the life-giving banks of the Nile River, the ancient Egyptians developed a creation story that was completely centered on water. Before anything else existed, before land, sky, gods, or humans, there was only Noon. Noon was an infinite ocean of dark, motionless water that contained all possibilities but no actual reality. It was a dark, silent, pregnant void. From these primordial waters, the first god, Atum, whose name means completeness, emerged. Different texts say he willed himself into existence, or just rose up like a bubble on the surface of the water. Atum's first problem was finding something solid to stand on in the endless ocean. So he created the first dry land, a primordial hill called Benben, which rose from the waters. This hill, often pyramid-shaped, became the model for all later Egyptian pyramids. Standing on this first land, Atum began the work of organizing the chaos. He sneezed out Shu, the god of air, and spat out Tefnut, the goddess of moisture. These two represented the first separation of elements from the undifferentiated water of Noon. Shu and Tefnut had their children of their own, Geb, the earth god, and Nut, the sky goddess. But Geb and Nut were born locked in a passionate, unending embrace, which prevented any space for life to exist between earth and sky. Atum commanded Shu, the air, to separate his children. Shu positioned himself between them, holding up Nut, the sky, while Geb remained below as the solid earth. This separation created the fundamental structure of the Egyptian cosmos. The waters of Noon didn't disappear. They remained as the foundation underlying all existence, surrounding the created world on all sides. The ancient Egyptians believed the Nile River, the lifeblood of their civilization, was connected to this primordial ocean. The predictable, life-giving annual flood of the Nile was understood as a reenactment of the original creation, when ordered fertility emerged from the chaotic waters. The earth was a beautiful, ordered island floating eternally on a sea of potential chaos. In Mesoamerica, the creation myths of the Maya and Aztec peoples took on a dramatically different, very scary, and very bloody character. They didn't see Earth's formation as a single act, but as the result of ongoing divine sacrifice, where the gods had to repeatedly destroy and remake the world through their own suffering and death. The Aztec story describes Earth's formation through a cosmic battle with the Earth monster, Tlaltecuhtli. This primordial creature was a massive crocodile-like being floating in the dark waters, covered with mouths that demanded constant feeding. The two great gods, Tezcatlipoca, smoking mirror, and Quetzalcoatl, feathered serpent, looked at this monster and knew no ordered world could exist. They had to defeat it through sacrifice. Tezcatlipoca allowed the monster to tear off his foot to get close enough for the attack. Then, together, the two gods literally tore the monster apart, stretching its body in opposite directions until it split in half. From the monster's body, they created the current world. Its skin became the Earth's surface, its hair became the forests, its eyes became the caves, and its mouths became the rivers. But Tlaltecuhtli wasn't truly dead. The Earth was still alive, still hungry. The monster's many mouths continued to demand blood and hearts, which is why the Aztecs believed that human sacrifice was necessary to keep the world functioning. If they stopped feeding the Earth monster, the world would end. Their calendar reflected this terrifying philosophy. They believed the current world was the fifth sun, the fifth attempt by the gods to create a stable reality. Each previous world had been destroyed by an angry god. The current sun, the one they lived under, demanded constant nourishment through human blood to prevent the world from ending in earthquakes and darkness. The Mesoamerican story tells us that creation is not a gift, but a bloody, ongoing process that requires constant payment and sacrifice from every generation. Across the vast expanse of North America, from the Arctic to the Gulf, hundreds of distinct indigenous cultures shared a remarkably similar and beautiful creation story, the Earth Diver myth. The core image is simple, yet profound. A small animal diving to the bottom of a primordial ocean to retrieve a handful of mud that would become the entire Earth. The world begins covered entirely by water. Various animals swim in this endless ocean, but they long for a place to rest, to build homes. In most versions, it's the animals themselves who take the initiative. The largest, strongest animals, the loon, the otter, the beaver, all volunteer first to dive to the bottom, but they fail. The water is simply too deep for them to reach. Finally, the smallest, seemingly least capable animal volunteers, the muskrat. Tiny compared to the others, and not known as an exceptional diver. The other animals are skeptical. Down into the dark waters the little creature goes, staying submerged much longer than any of the others. When the muskrat finally floats to the surface, seemingly drowned from the incredible effort, the other animals see that its tiny paws clutch a small amount of mud from the ocean bottom. The transformation varies. In some versions, the great turtle offers his back as a foundation, and the mud is placed there to grow into Turtle Island, the Native American name for North America. In others, the mud is placed on the water's surface and begins expanding in all directions through spiritual power. This myth is all about humility and cooperation. The smallest, humblest creature succeeds where the most powerful could not. It teaches that solutions to great challenges often come from unexpected sources, and that the creation of Earth was a community project that established patterns for how all subsequent life should be lived. Humans are not given dominion over other creatures, but are understood as younger siblings who depend on the wisdom and sacrifice of their animal relatives. The Earth is a community built on cooperation, and we are just one part of it.
In 2016, the Standing Rock Sioux tribe protested the Dakota Access Pipeline, arguing it threatened their water supply and sacred sites. During the protests, elders repeatedly invoked the Earth Diver creation story, saying, "We are water protectors because water created the Earth." What struck me was how this ancient myth, thousands of years old, had become a framework for modern environmental activism. The story wasn't just about the past, it was a living philosophy about humanity's relationship with Earth. Meanwhile, scientists studying the protest published papers showing the pipeline route did indeed threaten watershed systems and archaeological sites. The myth and the science were saying the same thing. Water is sacred because it is literally the foundation of everything. The indigenous protesters weren't anti-science. Many of them were citing hydrology studies. They were using both the ancient story and modern data to make the same argument. It was one of the first times I truly understood that mythology isn't the opposite of science. Sometimes it's just science's elder sibling, teaching the same truths in a different language. The Earth Diver myth survived for millennia because it encoded a fundamental truth. Water creates and sustains all life. That truth doesn't become less true when you translate it into hydrology and biology. It just becomes more detailed. I'll be honest, I used to be pretty arrogant about mythology. When I first started studying cosmology, I looked at creation myths and thought, how quaint, how primitive. Now we know the real story. I genuinely believed that science had made mythology obsolete. But then something happened that changed my perspective. My daughter was 5. And she asked me where the Earth came from. I started explaining the Nebular Hypothesis, gas clouds, gravity, accretion, and watched her eyes glaze over. She didn't understand. Worse, she didn't care. So I tried a different approach. I told her about the Native American Earth Diver story, about the brave little muskrat who dove deeper than anyone thought possible to bring back the mud that became the world. Her eyes lit up. The muskrat was small, like me, she said. She got it. The meaning of it. That courage and determination matter more than size. That everyone has a role to play. That the Earth is precious because it was created through sacrifice.
The scientific story gave her facts she couldn't contextualize. The mythological story gave her a framework for understanding her place in the world. And I realized these stories survived for thousands of years not because ancient people were ignorant, but because they were wise. They understood that humans need more than mechanisms. We need meaning. We need stories that connect us to the world emotionally, not just intellectually. I still believe the Nebular Hypothesis is correct, but I also believe my daughter learned something equally true from the muskrat story. And I'm not arrogant enough anymore to say one truth is superior to the other. Creation myths from different cultures are like different languages describing the same sunset. Imagine people from around the world watching the sun set over the ocean. An English speaker says, "The sun is setting." A Japanese speaker says, "Higa shizumu." A Spanish speaker says, "El sol se pone." They're using completely different words, different grammatical structures, different sounds, but they're all describing the exact same phenomenon. They're all true. Now, imagine someone insisting that only the English description is correct, and all the others are primitive or wrong. That would be absurd. The sunset doesn't care what language you use to describe it. Similarly, creation myths are humanity's attempts to describe the mystery of existence using the cultural languages available to them. The Norse describe it through violence and sacrifice. That's what they knew. Harsh winters, constant struggle. The Egyptians describe it through water and fertility. That's their reality, the Nile's annual flood. The Hindus describe it through endless cycles because their philosophy embraces eternal return. They're all looking at the same cosmic sunset, the profound mystery of why is there something rather than nothing, and describing it in their own cultural language. None of them are wrong. They're just different translations of the same ineffable truth. And maybe, just maybe, the scientific description is simply another language, the language of mathematics and evidence, translating that same sunset into yet another form. All true, all valid, all describing the same beautiful, mysterious reality from different perspectives. But here's the question that haunts me late at night. What if all of this, the science, the mythology, the entire 4.6 billion year story, is just one layer of reality? What if Earth's formation isn't the beginning of the story, but a chapter in the middle of something much, much stranger? What if the real question isn't how did Earth form, but is Earth even real? Hold on to something because we're about to go down the rabbit hole.
So we've walked the path. We've seen the science, from the slow gravitational violence of the Nebular Hypothesis to the unbelievable life-creating accident of the giant impact. We've seen the mythology, from the body of the Norse giant Ymir to the patient shell of the Hindu cosmic turtle. But all this knowledge, all these stories, lead us to the final, most mind-bending question of all, one that takes us from the Earth's core to the very limits of reality. Which one of these stories is the truth? Maybe the truth is all of them at once. Maybe the truth isn't about gravity or gods, but about information. Modern physics has given us a completely new kind of creation myth, the simulation hypothesis. This idea suggests that our entire universe, including Earth, and everything we consider real, might actually be an artificial simulation running on unimaginably powerful computers built by some incredibly advanced civilization. Think about that for a second. If this theory is correct, then Earth didn't form through cosmic processes at all. It was programmed into existence. The Big Bang was just the start of a cosmic computer program. The formation of galaxies and stars and planets, the execution of the program over cosmic time. Why does our universe seem so ridiculously perfect, so fine-tuned to allow for the formation of stars, planets, and life? Because it was literally designed that way by programmers who wanted to create a reality where interesting things could happen. The physical constants that govern everything, from atomic structure to gravity, are perfectly balanced because they were programmed to be. Think about our own technological trajectory. In just 70 years, we went from computers that filled entire buildings to devices in our pockets that are billions of times more powerful. We've created increasingly sophisticated virtual realities, video games where you can explore entire planets.
where physics works realistically, where AI characters seem almost alive. Now extrapolate that progress forward not 70 years, but 7,000 years, or 7 million years. What could a civilization with that much technological advancement create? They could create simulations so detailed, so perfect, that the beings inside them, us, would have absolutely no way to tell the difference between the simulation and base reality. Every atom could be simulated, every quantum interaction, every thought in your brain. The entire 13.8 billion year history of the universe could be rendered not in real time, but as a complete, internally consistent program. Here's where it gets truly disturbing. If it's possible to create such simulations, then statistically we're almost certainly living in one. Think about it. If one advanced civilization can create detailed simulations, they could create thousands of them, maybe millions. And those simulated civilizations, once they advance enough, could create their own simulations. And those simulations could create simulations. Simulations nested within simulations like infinite mirrors reflecting each other. So you end up with this: one base reality and billions or trillions of simulated realities. If you had to guess which one you're in, the math says the odds are overwhelmingly in favor of simulation. You're vastly more likely to be in a simulation than in the one true base reality. The Earth we know and care about would still be our home. Your experiences would still be real. Your love, your suffering, your consciousness, it would all be valid, whether it occurs in a biological brain or a simulated neural network. But the origin? It wouldn't be a collapsing dust cloud. It would be a line of code. Our beautiful, perfect blue planet would be the most sophisticated piece of creative work ever conceived, a complete world with billions of years of apparent history, created by programmers who are artists on a cosmic scale. And here's the truly unsettling part. There's no way to prove we're not in a simulation. Any evidence we discover, any experiment we run, any observation we make, it's all happening within the system. It's like a character in a video game trying to prove they're in a game. They can examine the physics of their world, study the formation of their planet, trace their history back billions of years, and it would all be consistent, all be real within the rules of the game, but it wouldn't tell them anything about the reality outside the game. Some physicists have suggested we might find glitches, places where the simulation breaks down, reveals its underlying code. Others say if we're in a simulation sophisticated enough to fool us completely, there wouldn't be any detectable glitches. The programmers would have debugged them all. From the simple, elegant theory of a spinning cloud, to the complex, violent philosophy of a giant's death, to the ultimate idea that we might just be code, the story of Earth's birth is the single greatest narrative ever told. It is a story that reveals the universe is not just stranger than we imagine, but stranger than we can imagine. The rocks tell one story, the old gods tell another, and the physicists are writing the third. But every single one of them is an answer to the same single human question. How did we get here? In 2003, a philosopher named Nick Bostrom published a paper titled, "Are You Living in a Computer Simulation?" that would change how scientists think about reality. But here's the weird part. Bostrom wasn't the first. In 1977, decades before the simulation hypothesis became mainstream, a science fiction author named Philip K. Dick gave a speech in France where he claimed he had experienced a revelation that we're living in a computer simulation created by entities in the future. He described it in detail: reality as software, time as programmable, history as mutable code. The audience thought he'd had a mental breakdown. Dick died in 1982, dismissed as a paranoid eccentric. Fast forward to 2016, Elon Musk declares at a tech conference that the odds we're living in base reality are 1 in billions. Suddenly, what seemed like the rantings of a disturbed sci-fi writer is being seriously discussed by physicists and tech billionaires. Dick's breakdown looks a lot more like prescience. The simulation hypothesis went from fringe lunacy to mainstream philosophy in one generation. And it makes you wonder, how many other crazy ideas are we dismissing right now that will be conventional wisdom in 50 years? What if the crackpots are right, and we just can't see it yet?
The simulation hypothesis terrifies me in a way nothing else does. Not death, I've made my peace with mortality. Not cosmic meaninglessness, I find meaning in human connection regardless of cosmic purpose. But the simulation hypothesis strikes at something deeper. The reliability of reality itself. If we're in a simulation, then everything I think I know, every memory, every experience, every relationship, could be code. My daughter's laugh? Rendered audio. My wife's touch? Simulated sensory input. The grief I felt when my father died? Programmed emotion. And here's the thing that keeps me up at night. It wouldn't matter. Even if it's all simulated, it still feels real. The suffering is still real to me. The love is still real to me. But there's this nagging voice that says, what if they shut down the simulation tomorrow? What if you're not even a persistent entity, but something that gets spun up fresh each morning with implanted memories? I hate thinking about this. I actively try not to, because once you start down this path, there's no logical stopping point. Solipsism and simulation and dream logic all blur together. So I've made a choice. Maybe it's a coward's choice. To just act as if reality is real. To treat my experiences as valid. To love my family. Pursue knowledge. Try to be good. All while accepting that I have absolutely no way to verify that any of it exists outside my perception. Maybe faith isn't about believing in God. Maybe faith is believing in reality itself. And maybe that's the hardest faith of all. Understanding the simulation hypothesis is like being a character in a novel trying to prove they're fictional. Imagine you're Sherlock Holmes. You're brilliant, logical, observant. You start noticing patterns, coincidences that seem too perfect, plot holes in your world's history, the fact that nothing significant ever happens when Watson isn't around to document it. You begin to suspect, what if I'm not real? What if I'm a character in a story? So you investigate. You examine the physical laws of your world, Victorian London. You trace your personal history. You study chemistry, physics, deduction. Everything checks out. The world is internally consistent. You have memories stretching back years. Other people confirm their independent existence. And yet, all of that would still be true even if you were fictional. Arthur Conan Doyle created a complete, consistent world with its own history and physics. The fact that it's consistent doesn't make it real. It just makes it well written. You, Sherlock Holmes, have no way to access the real world of 1890s London where Doyle sits at his desk writing you into existence. You can't step outside your own story. And if you somehow became aware you were fictional, what would change? You'd still have to solve crimes. You'd still care about Watson. Your experiences would still matter to you, even if they're just ink on paper to someone else. That's the simulation hypothesis. We're potentially characters trying to prove we're in a story using logic and evidence that only exists within the story itself. The investigation is impossible. And maybe that's okay. Maybe Sherlock Holmes doesn't need to know he's fictional to live a meaningful life. Maybe we don't either. The most incredible part of this entire journey is that the conversation continues. The wonder never ends. Whether we are products of stellar dust or a divine word or cosmic computation, we remain the universe's way of asking questions about itself. Every story we've explored, from the collapsing nebula to the slain giant to the cosmic code, is humanity reaching for the same truth. We exist, and we want to know why. The specific answers change, the scientific details get refined, the mythological meanings shift and adapt, but the question remains eternal. Maybe that's the real answer. Maybe the point isn't to find a single, final explanation for Earth's origin. Maybe the point is that we keep asking. That we're the kind of creatures who look at the moon and see not just a light in the sky, but a cosmic scar that demands explanation.
that we're capable of tracing our origins back through 4.6 billion years of violence and creation and impossible luck. You're standing on a planet that shouldn't exist, orbiting a star that's one of billions, in a galaxy that's one of trillions, contemplating your own existence? That's not just unlikely. That's not just improbable. That's miraculous. Whether the miracle comes from gravity, gods, or computer code. The Earth formed from dust. The Earth was carved from a giant. The Earth was programmed into existence. All of three are true. None of them are true. It depends on what you're asking. But here's what I know for certain. Right now, in this moment, you're alive. You're conscious. You're aware of your place in this vast, strange, beautiful cosmos. And that awareness, that spark of consciousness that lets you ask, where did I come from, might be the most important thing in the universe. Because maybe we're not just asking where Earth came from, maybe we're asking where we came from. And maybe, just maybe, we're asking because somewhere, deep in our DNA, in our atoms, in our code, we remember. We remember being stardust. We remember the cloud. We remember the violence and the creation and the long, slow climb from nothing to everything. You are 4.6 billion years of cosmic evolution that has learned to look back at itself and wonder. That's the real story. Not how the Earth was born, but how the Earth became aware of its own birth. How matter became mind. How dust became dreams. Welcome home. You're made of stars, built from violence, stabilized by accident, and conscious against all odds. You're the universe's way of understanding itself. And that, ultimately, is the answer to every question we've asked.
Tap the subscribe button. Keep asking questions. Keep wondering. Because the story of Earth isn't over. It's still being written, and you're part of it. But wait, there's one question we haven't answered. If life survived the late heavy bombardment by hiding in deep sea vents and underground chambers, what does that tell us about life on other worlds? Could there be entire biospheres thriving beneath the ice of Europa or Enceladus right now? Could Mars still harbor life in underground aquifers? And if the simulation hypothesis is correct, why would the programmers bother simulating bacteria on distant moons? Unless the simulation isn't for us. Unless we're just background characters in someone else's story. But whose? Some questions don't have answers. They just lead to better questions. And maybe that's exactly as it should be.